President and founder of Chicago Quantum. I'm here to talk today about a presentation that we just gave on a research collaboration, kind of a knowledge sharing, on our new paper. We submitted it to arXiv yesterday. It should be out in the public domain August 21st of 2020. So I wanted to talk a little bit today about the work we've been doing. This is our 60 asset publication. So we're doing portfolio optimization on a quantum computer, but also on using classical solvers, things like simulated annealers and genetic algorithms and fat-tailed Monte Carlo analyses to pick that best stock portfolio for a buy and hold strategy. So I'm going to walk you through it today. This is not a highly technical discussion. You don't need a PhD to be able to follow it, and but it will get into some of the good detail. So we're optimizing portfolios of 60 stocks. What that means is we're finding the highest return from those stocks based on how it did for the past 12 months with the lowest amount of risk or volatility in the return that you have. So hopefully you avoid the downside while you still make money on the upside. So what did we do? We had to reformulate the Sharpe ratio. We had to change it to run on a quantum computer. And the reason we had to do that, actually we had a question when we talked about it today. We do that because quantum computers use linear algebra. You feed it a matrix and it comes back, but it really only does addition and subtraction. The problem is they don't do multiplication and division. And we actually even tried to do to turn a Sharpe ratio into a subtraction problem by using natural logs, but you end up having to do a Taylor series expansion, and there's an error term, and it just doesn't work well. So make it a subtraction problem. There's no errors at all. It works great, and actually it works great on a classical simulator, classical solvers as well. We scale the problem from 40 to 40 assets. We thought 20 was a lot. And then we get to 60 assets and 60 stocks, and that's actually working really well. Now, 60 stocks has 2 to the 60th portfolios, or 1.15 times 10 to the 18th portfolios. That's about a quintillion portfolios. It's too much to do brute force. We use 5 classical solvers and the DWave to find the ideal portfolio. They all take less than a minute. The ideal portfolio, which is the best one that we found, doesn't necessarily mean the best one, but the best one that we found, it outperformed the market after 2 weeks and 5 weeks. So net, investors can either use classical methods, which use Python. These are actually non-proprietary methods. You just code yourself. I mean, we can work with you. Or you can use a quantum annealing computer by DWave to build efficient equity portfolios. And then we have 3 artifacts. We have our 40 asset article, which is on arXiv, how we pick 60 stocks in a Medium article, and then our 60 stock article in arXiv. And we will continue our research. We're going to scale to 100 or more assets. We're going to add new investment types, and we're going to explore quantum walks on graphs in addition to quantum annealing. So what is this new formulation? Guys, Chicago Quantum, why wouldn't you use the Sharpe ratio? It's been used since the 50s. It's 70 years old. It works great. Come on. Well, the truth is, we wanted to use a Sharpe ratio, but we couldn't. Quantum annealing computers cannot divide, but they can subtract. And so what we did a couple of things. Over to the left-hand side, you see right here, you have a Sharpe ratio is the weights of all the stocks times the beta of the stocks times the expected return of the actual risky part of the stock minus the risk-free rate of return. So that's your benefit of holding the stocks in the market. And then add back the risk-free rate of return, and it's divided by the standard deviation of the portfolio. That has a lot of nominal terms in it, a lot of things that have inflation or that have just like money in it. So what we do is we create a simplified ratio called the Chicago Quantum ratio, and that's the weight of the stocks times the covariance of the stock times, versus the market benchmark. And so if I have my covariance of the actual stocks against the market, and I divide that by the same thing, standard deviation of the portfolio, I get a Chicago quantum ratio. Why would I want to do that? It's less jittery and it's less volatile than the Sharpe ratio. It's a little bit easier to calculate quantitatively, but actually it just gets rid of things like a 7% interest rate, or stocks are up 12%. And so this way you're just looking at hardcore market momentum. On the right-hand side, you see the Chicago Quantum Net Score. This takes the variance of that market, kind of, the basket of stocks or the portfolio, and you subtract off the expected return raised to a power. And we do that to roughly equalize the impact of variance or risk and return on a portfolio. And so this works great. This is a buy and hold strategy based on 12 months of historic data. So how do you know it works? We love this formulation. It works great. And so the shape that you see here is an efficient frontier. If you search EFF or efficient frontier or efficient frontier Monte Carlo or efficient frontier Python in Google right now, you're going to see shapes like this. And what they're going to say is that the outside curve, upper left, is the efficient frontier. Those portfolios are the most efficient. You get the most expected return for any given amount of standard deviation or risk. So you could never really hope to do better than the efficient frontier. So what we found is if we just have the DWave find us two portfolios, we're looking at 30 stock answers, they're about average. Those two portfolios are highly efficient. They're right at that efficient frontier as determined by 115,000 runs of a Monte Carlo analysis. The blue dot is our genetic algorithm. This was the best answer that the genetic algorithm can give us. Now you look at that same data set and you have 30 DWave suggested portfolios. They're right at that efficient frontier again. You take it to 150 and you see that actually the DWave is proposing portfolios that are actually better than Monte Carlo analysis. In that case, it's 20,000. So 150 is doing better than a 20,000 run Monte Carlo. If you take it up a bit, 414 portfolios against 40,000 Monte Carlo, and you're kind of blowing away the efficient frontier at the higher end. So I think what's happening is a Monte Carlo analysis is looking for most of its values, most of its portfolio sizes at n over 2 or half. So if it's a 60 asset portfolio, they're looking for portfolios, let's say 20 to 40 stocks. Our quantum computer is smarter than that. It's looking where we tell it to look. So we tell it to look at small portfolios, large portfolios in the middle. And as we start to find smaller portfolios, we can start to build better answers than even found in Monte Carlo. And that's what you see right here. Now, the data sets we use for our papers, one of them is 2588 and the other is 3556. You see that 2558 and 88 DWave responses are in red. Almost completely cover the efficient frontier that's in yellow, and the yellow is 221,000 plus portfolios that were found not just through Monte Carlo, but through a fat-tailed Monte Carlo. And one of those yellow dots, by the way, is the best answer you can find. And in fact, one of the red ones is one of the best answers you can find. And the genetic algorithm finds the best answer you can find. So we have the DWave very quickly finding answers that are effective. If you look down at the bottom, you see after 3,556 data points, it's almost completely covering the efficient frontier. So it doesn't take many runs of the DWave to give us answers that are right in the ballpark of the efficient frontier. So what did we accomplish as a team? We kept our focus on U.S. highly liquid equities. that are continuously traded. In the case of our 60 asset paper, it's 254 days. We solve a 40 asset universe on a quantum annealing computer, and we compare the performance against classical options. So the first time we did this, the classical options weren't as good. And so the comparison, the DWave was right in the middle, but in fact, we even use brute force because you can still use brute force in a 40 asset universe. As it gets to 60 assets, we then solved it for a 60 asset universe. And we compared the DWave's performance against very much improved classical options, but also some hybrid options. And one of them is a hybrid classical quantum solver. So our classical custom coded work, we coded a simulated annealer that basically pretends like it's a quantum annealer, but it's not quantum. It's a digital annealer. We have a genetic algorithm, and that is using parents that breed children that take the best attributes of a portfolio and pass it down. And a Monte Carlo fat-tailed is doing random sampling, but it's sampling in each size of a portfolio, a very small amount. So in 220,000 kind of throws of the dice, you most likely will find the best answer if the best answer is a very large or a very small portfolio. We also run some additional DWave samplers. You see a simulated annealer. DWave has one. They have a taboo sampler, a multi-start and stop sampler, and then they have a hybrid solver, and we've run all three. And so this is great. We were able to get it done, 60 assets, and compare the performance. And then we understand the challenges now much better, the challenges to continued scaling. Our plan is to go to 100 assets and then potentially up to 500 assets on the DWave. So what's the answer from our initial analysis? Well, firstly, to the lower left, 6 methods solved the problem, and they solved it in less than a minute. And these are using non-proprietary methods, so they're not for money type solvers. They're free. Either we wrote them or DWave let us use them, and it's great. So a genetic algorithm solved the problem. So yes, it found the ideal portfolio, and it found it in 7 seconds. Now, normally, if we were to feed the genetic algorithm with DWave, it should be faster. For our research paper, it took 48 seconds. We might have had a memory issue because I just ran the same experiment this morning, and it took 7 seconds for random seeding of a genetic algorithm, but it only took 6 seconds for the DWave. So that would be 7 and 6. The DWave simulated annealer solved the problem in 11 seconds. Our bespoke or custom coded simulated annealer solved it in 15. We're manually tuning this a little bit ad hoc. We think we can do better. I'm not sure we can get to 11, but we're at 15. The DWave quantum annealer took 21 seconds. So this includes all of the runs we did for system parameter checking, for calibration time, and this is an aggregation of all the runs for all the time to do all these experiments for this paper. We would expect this number to be 15 seconds of computation time moving forward. But in the experiment, it was 21. Our Monte Carlo fat-tailed analysis did find the best answer, and it ran for 24 seconds. That was 221,000 samples. What's interesting is the taboo sampler really was more of a random sampler, at least the way we ran it. It only really found scores around 20 to 40 assets, very similar to a random Monte Carlo. It ran for 267 seconds, and it actually had terrible answers. And the DWave hybrid sampler, we ran it for 5 seconds. It didn't find any valid portfolios. Every run we did was unsuccessful, and so for us, this is not a good method or model. And the details of the analysis, these are the 60 stocks that we ran. You can see them up here. We do a risk-free rate of return. We have 4 different indices that we take the average of. So the overall market return for the 12 months prior to our analysis is 18.6%. So it's a very much an upward-facing market. The variance of the market benchmark is a little high at 0.00045. We would expect to see something like 0.00040. And so it's kind of an active market right now, and the beta range of the 60 stocks is 0.42 to 2.1. And so, and this is what the 60 asset portfolio looks like. Initial results. So, what did you get? Right? So, over to the right, you see the same solvers. Um, we did also add the DWave quantum annealer with our Chicago quantum ratio solution. You see the best assets or portfolio found. So when we allowed it to find one asset, which we typically don't, it picks APA, which is Apache, out of the 60. When you allow it to pick two or more, it picks AMP, Ameriprise, and Apache. Pretty consistently across the models. In the case of our simulated annealer, it found APA, but it also found a four asset solution. And then you see the different scores. And so we're pretty consistent. We're validating the D-Wave answers pretty nicely with our classical models. And you see that the D-Wave Tableau sampler has what looks to be about 30 assets that it chose, and a very, very poor CQNS score. See, the CQNS negatives better, more negatives more better. And so negative 0.05 or 0.06 is great. 0.005 is 10 times worse. And if you look at the 60 asset solution, it's a 0.01. So it's actually not a very efficient portfolio, which is what you'd expect. Now, if you look to the lower left, you see that the ideal stocks, which in this case is AMP and APA, again, Ameriprise and Apache, returned almost 14% during the last 5 weeks. All the 60 stocks returned 7. Our CQR portfolio returned right about 7. The S&P is 6.2, and the CQNS stocks at 5.3. So we're kind of in the market range when we allow ourselves to use larger portfolios. We kind of water it down because most people wouldn't want to just hold two stocks. But when you just hold those two stocks, they do great. 14%. They outperform the market by almost 7% or 700 basis points. That's tremendous. And so, could just be beginner's luck. We're going to keep measuring and we're going to keep working to come up with even more new portfolios. So, what are our goals for 2020? I am the president of Chicago Quantum, and so where are we focused? We're focused on scaling to a 100 asset universe. If we could solve with one throw of the dice 100 assets and find the best portfolio, that makes something like the S&P 500 a little easier to get your teeth around. And we're going to compare performance against even more improved classical and hybrid options. We do expect problems at 72 assets on the D-Wave. We do. And part of it is it's just not enough qubits, at least in the 2017 architecture that we have access to. We're going to add diverse asset types, things like fixed income or bonds, commodities, currencies like Bitcoin, and even real estate investment trusts. And we are going to evaluate shorter duration investment horizons. We're also going to immediately start evaluating quantum walks on graphs. So quantum walk on graph uses probability theory, but also with quantum effects, to possibly have information move faster, to possibly allow us to forecast tomorrow's stock price. Now, our hypothesis is that quantum walks on graphs is great. We're going to make a ton of money. We're going to figure out how to forecast the future. Oh my, we're going to be wealthy, right? It's our hypothesis. We have no evidence that it actually will work, and so that's the research we're going to do. It's the second basically of the third computing paradigm: annealing, quantum walks, and gate model. We're leaving gates for last. The last thing we want to do is we have a goal to earn revenues by serving real enterprise clients. They could be companies, they could be government agencies, they could be research houses, they could be investment managers, asset managers, money managers, or even large individual investors, because we want to grow the team and we want to build even more quantum capabilities. So now I'm going to give you some interesting details. So For those who maybe aren't interested in energy landscapes and quantum computers, you could start to tune out. But I find this stuff fascinating. The first is the scale challenge. So, Jeff, why can't you get to 100 assets? Why 60? I get that question all the time. Well, so the challenge is that we're feeding the D-Wave computer a matrix. So the matrix, here's a real matrix for 59 out of 60 assets. We have to send it a different matrix for every size portfolio. And the linear terms you see are negative, right? So negative 0.5, 0.3, 0.2, 0.5, 0.8. By the way, the biggest one, which is hidden there, is 0.9. But the quadratic terms, the ones that aren't on the linear, the diagonal, sorry, are really small, 0.0037, 0.036, 0.04. If you were to see this matrix for 2 or 3 assets, the quadratic terms are almost the same as the linear terms. And so what happens is the D-Wave is an analog system. It's looking for energy levels and energy landscapes. It's like a mountain climber at the top of a mountain trying to get down a hill. And when there's a lot of energy diversity, think of it as ridges and holes that you can put your feet and your hands in. You climb down the mountain. When the energy landscape looks like this and these numbers are so small, the footholds and the handholds are tiny. They're like the size of a bird's beak or, a small rock. And so you could barely get hold. And so what you're going to find yourself doing is sliding down the hill. There's nowhere to grab hold. There's no equilibrium to find, or at least it's hard to find that equilibrium without taking a very long time. So that's challenge number one. Challenge number two, this is a diagram on the right of the DWave Inspector. This is a tool that DWave allows you to use. And so this is the loading of an actual 58 out of 60 asset cubo. It pretty much looks the same for 30 assets too. And you can see there's lots of dots and lines in there. Well, those dots are qubits that are being used up. And we're using up somewhere between 1,300 and 1,700 qubits on average out of the 2,048 that are installed. The yellow is the connectivity that one asset needs to be able to talk to all the other assets. And so if we want covariance and we want to compare IBM stock versus Intel stock, then they've got to touch each other. And so in this case, just to have one asset touch all the other assets, you need to have it going through 20 different qubits. It's a lot. Part of this is because of the limited connectivity. When you look deeply into the actual physical architecture, you see these little shapes. There's 8 qubits, and they talk to each other really well, but there's limited connectivity between these cells of qubits. And that's why you have all these chains. And so these chains break over time as well. They're more like spider web than they are pieces of steel. And so if you're going to run a pretty long job, they start to break, and once they break, you lose some connectivity. So this is another scale challenge, is we're running out of qubits. On the positive side, what did we do that really worked well? So what happens when you just load the qubos, the data, the expected returns and the variance, and you say to DWave, hey, go give me some answers. The answers come out in blue, but they're supposed to be right where the orange is. And so what happens is you don't get the answers that you'd like to get. In fact, if you look at that separation here, you're asking for 50 assets, and your best alternative there, it's like way down there, like 40 assets. So you're not even getting one portfolio that matches. So then we do an affine transformation. We call this shifting. We shift the cubo by putting penalties on all of the answers that aren't exactly what we want. Once we do that, now you see this orange, and the blue is centered around it. And there's a little bit less spread. We want less spread, and we want the orange in the center. And as we do a graduated affine transformation, you can see that the blue follows the orange. It is right around, and there's actually really good answers that are underneath the orange. You just can't see them. And so by doing a graduated affine transformation, we get better, more efficient answers out of the DWave. The other thing we do is we've come up with a new way to um, random sample. So a Monte Carlo is just, hey, roll the dice, right? Let's test. Fat Tailed says, I want many, many more tests outside of the n over 2, so outside of 20 to 40 assets. And I want Monte Carlo to find me answers in 2 assets and 3 assets and 4 assets. And I want him to find it in 57 assets and 58 assets and 59. And what happens when you do that, and you don't even need that many assets, is you start to find really great answers. So the Chicago Quantum Net Score, smaller is better. So look at that. I'm finding answers that are just terrific. Terrific answers. And they're in the smaller portfolio sizes. So that means I could focus my attention on the smaller asset sizes. And you see there's like an asymptotic relationship here, whereas you get larger and larger, these are 60 asset portfolios or 58, 59. They're all right around that negative 0.002, but the best ones are negative 0.004, negative 0.006, there's even one negative 0.007. So we want to capture those. We'll still search the entire space, but it gives us a sense of where the best answers, by the way, and the worst answers are as well. So you can't just pick randomly a small portfolio, you have to pick the best one. Now I'd like to introduce you to the team. So this is our Chicago Quantum team. These are the primary associates. We have others who volunteer and who work for us or work with us, collaborate with us, but this is the core team. And so you got Jeffrey Cohen, myself. Clark Alexander is a PhD in mathematics, has a teaching background, and spends full time doing data, very complex data analytics for clients. And then Alex Kahn is an IT executive with an insurance background who also made the switch over to quantum computing, has a certificate from MIT, and has been really focused on this as well. And so we are U.S. Advanced Computing Infrastructure Inc. We have a website. We're very active on Twitter, Dunn's Engage number, and we are proud of our Better Business Bureau rating of A+. So I want to thank you very much. Thank you for listening. If you have questions, please give me a call. In fact, on my other screen, I see somebody did just give me a message or a question about our paper that's coming out. And so thank you very much. I really appreciate you spending the time and listening to this session. Bye-bye now.